Okay, my friends, get ready for this. This is going to be a lot of fun for me. I have been talking about my dipole electron flood theory and how it accounts for the redshift. And now they're fighting back. What is the redshift? This is called the Explainer by Science Alert staff. That's a magazine that puts out all the latest in the science. And I've been basically going against their research because what they do is they go for peer review. And if the peer review doesn't accept it, well, then they don't put it in the paper. So I'd like to see them respond to my stuff. Let's find out what I have to offer. Okay, my wonderful friends, get ready for this. This is Science Alert. I comment on their claims virtually every day, and they have been commenting back against my claims against their claims. And this is their claim about what is the redshift. I've been making my point. The redshift is nonsense, and I'll explain why, and I have examples that I can show. They claim the redshift is, as academia claims, it's a response to the universe expanding because of the Big Bang. The redshift is a red herring. They're using it to make it sound like, oh, it's just natural, everything expanded from nothing. It's just absolute nonsense. And the redshift is strictly because light is slowing down, not because it's being pulled away. Let me explain. All right, this is why I feel I have every right to be able to speak in this realm. I did all of this stuff. This is all real old stuff. I mean, this goes back to early 70s, 1968. I was in the Army. I serviced 90 Hercules missiles. And I came up with the transfer of energy is from light into atomic vapor, and it is. And that atomic vapor, it makes plants grow, it makes things heat up, it does everything. And it has there is a substance to it. There is a weight to it. And I did all this stuff. I did all the way to the chemistry, and as deep as you can get into this, I got into everything, because you have to. If you don't, you get into one little bit and piece, you're into nowhere. So I have every right to be speaking about this, and I am going to speak about it. And the redshift is strictly light slowing down, and I can prove every word I'm saying. I don't make the statements without the proof. All right, this is why they're talking about the redshift. Why is the redshift useful in astronomy? Redshift tells us two things in astronomy. The first is no matter where we look into the far, far distant objects, these light that we can see, they're moving away from us at great speed. They're just flying away. It means either everything is being pushed away from Earth and we're standing still, or everything is being pushed apart from everything else. There is no way to account for what they say. You say you look this way, that's all going away. You look the other way, it's all going away. So we had to be the center of the universe according to this theory. It's not right whatsoever. Redshift is because light is slowing down. I can show you light slow down. See, now they're saying that there's no question light can't slow down, so it has to be shifting away, being pulled away. And they show this representation of what it would look like. The light is being pulled this way because the universe is expanding away. So instead of being nice blue, it shifts into the red. And here's exactly what they're talking about. I mean, the light does spin. It doesn't flap like a wave. They're saying here, blue is really tight. You see, they look like waves, but they're spinning. And I'm going to show you that. I could prove that too. So the blue is pretty tight. And they say that's because the sun or the light source is coming at you. And I could prove that too. This is amazing. I have proof for everything I'm talking about. So let's talk about the spinning part and the blue shift. I can show those. All right, the spinning part is right here. You see that? You go to a machinist and you ask him, what is that? And you know what he's going to say? That, my friend, is a drill bit. All right, that's a drill bit. And what it's doing is this here, right here. Spinning just like that. Some go way off to this side, some go over this side. You see how many there is? There is bazillions, zillions. Hold on. We turn that light off. And I turn this one off too. You can see better when it's dark, I believe. Now, you see all of those tiny little separations? Those are particles that push other particles away. Light does not want to be next to other light, the white particles. There's a black particle that has no problem being right on top of each other. This is what light looks like. These are photons. That's a photon. That's a photon. And it has a black and it has a white. Right? And the red is the very slow spinning particle. Green is quite a bit faster, and blue is off the charts. Now, I am showing you right now red accelerating, and here it is in its acceleration phase. Here's what we started with right here, a pulsed red laser. Light is light. I don't care. If it's light, it's supposed to go the same speed. I don't care what they say. And they do say that. And it has to plow through all these particles in front, pushing back against it. Well, we put it through a Venturi. And what a Venturi does is it accelerates things. And it accelerated the light right out of here. And then that's when we saw the particle. And then here it split the particle back to a black and a white particle. You see here? Right here, just before it smashed into the Venturi, we could see the particle. So the particle is here, and it's getting stronger and stronger. It's in a neutrino phase here, and now it's in the full photon phase. And then it exploded. So here's the full photon phase. Now remember, let's go through the neutrino phase. All right, here it's coming through the Venturi. Here it's not a complete photon yet. It's like it's building energy, right? It appears to me. Well, I know it is, because as it bounces against its own self, it's starting to glow. And here's more neutrino sideways. These ones are flat and these ones are sideways. I can't give you every little detail, but somebody could maybe. But at this point, they start to turn into a photon. And here is a little stronger photon. And then here it hits the Venturi and explodes. And the black actually separates from the white. And that I can show you as well. And somewhere I have it, but well, it's right here, but let me get you a better picture of that. Actually, this wraps it up pretty good. Fermilab, CERN, they see these same particles, but when they crash these huge particle things, they just see them in a bunch of debris. We started with them looking like this. You saw how they turned from a neutrino into the full photon. These are the two particles they see. But they see them in just a pile of stuff, so they don't really know that they were attached in this configuration. They really have never seen this in the way we see it, because we're using light, starting with it, which is the smallest particles that exist, basically, except these can be separated, and that's exactly what happened at the Venturi. You see here, they're tagged together, the black and a white, like two little bar magnets back to back. And it becomes semi-stable. Light is stable. It hits and bounces back. All right? One of these alone, a black and a white, is basically an electron. And that's not stable. That wants to incorporate into something. So when it hits something, it turns it into heat or that type of thing. It wants to glue onto something. They call them gluons. I'm not kidding. Now, this is the particle, and again, the same thing for Fermilab sees. Identical. This comes from, look it up, it's called point particle Fermilab. And these are the point particles, and these are the fixed particles. The fixed one never changes, the black one, and it doesn't. And I can show that right here. So what they're going to look for at Fermilab and CERN, here's what they look for, is the muon neutrino, the black one, to turn into straight muon, which it does, and the electron neutrino to turn into a shower. When it turns into Cherenkov radiation, which means it's like hitting heavy water, that's what they use it for. And they can see these sprays, and they know the electron shower creates a huge amount of energy, which it does. Luminosity is energy, and luminosity is off the charts. You see that? It started out here, you can't hardly even see it. And then it is accelerated, and light does accelerate, so Einstein was wrong. They're all wrong about all of this stuff. Light is a particle made of these two back-to-back dipoles, and it accelerates, and it gains energy. That's why they say the neutrinos go through their different flavor changes. They start as a vanilla ice cream, they turn into tutti frutti, and then they turn into rocky road, and then by the time you get home, it's strawberry. And it's just getting stronger and stronger and stronger energy until it explodes, that's all. And here it is exploded. These are the sterile muons, and these are the electron showers. Precisely, this isn't my doodle, I didn't draw that picture. That's from CERN. That's what they call a sterile muon and an electron shower. Electron shower is supposed to create enormous amounts of energy, and they will, because all you want is that white energy going into your battery, and then we've separated it. In order for any other way to separate the black from the white, you have to do mechanical work, and that takes energy. It takes a gasoline engine or something to make a generator run to push the electrons away from the other electrons. We've crushed the white ones, which can get small. You see how you got a big one here? And you got a small one? You see the big one, and you see all the white particles in front? That's because it's hitting those, and it's going to glow back. All right, once it disassociates from the black in this shower, this is the cat's meow, my friend. We should be able to get a virtually unlimited amount of energy from doing this. All right, you see, I told you I can show you the blue shift. Watch this. See, here's another thing I've been attacking them on. They show this. This came from the same place, gravity waves. We're all looking for gravity waves. Well, you see the black thing? You see, and this is a whitish looking thing, and they're looking for these fields. Well, here's these fields right now, and here's the blue shift. These gravity fields are everywhere, and every particle that's coming through it is being opposed. We have no idea where we are. They're taking light as being just going, never slowing down, the same speed, Planck's constant, light is constant. No, absolutely not. That's why we have the redshift, because light is just slowing down as it comes to us. That's all. Here's the blue shift. You see that? I told you I could show you the blue shift. And how does that happen? Well, this is the moon. And this was Rod Warren's nephew, Dylan Carpenter, took these pictures, just sent them to me, and that's about all I've ever heard from him, basically. He said, "What do you think?" And I said, "Wow." And I've been looking at them for a few years now, and these are all the dipoles. They're all dipoles, and they all have fields around them. And somehow he had some app that he had in this. He just got a new cell phone. This is, I don't know, a couple of years ago. Anyway, there's the blue shift. The moon is not spinning. A spinning anything in space creates a magnetic field. It just does. It has to plow through particles, and it appears to me it keeps charging and discharging, charging and discharging. Now, as the moon does not spin, it crushes the light in front of it and crushes it into the blue. When you crush the fields of light, you add energy to it. That's all you're doing, is adding energy. This is adding energy, and at the back, the energy is sort of dipping off. So we're crushing the fields in front. We're seeing it now as more energy. That's all that is. Blue shift, more energy coming out. Red shift, less energy. Okay, I don't think anybody can go against the fact that that is an acceleration of the particle of light. And I showed you the particle, and the particle keeps gaining energy. Back here it's in its neutrino floppy phase, and then it turns really bright and brilliant, which is the photon phase. And as it bounces back, the white is squirting through here. It's because it's a venturi. Venturi means it's a pinched, and the fields have to compress to get through. The white is the only thing once it can compress. The black can't compress, they're fixed. They bang, 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 but they won't let any black through, only the white. So you get these enormous electron showers, and to harvest them right here, all you're doing is accepting the white particles, and that's all you want. There should be no reason we can't get enormous amounts of energy from this. Okay, my friends, once again, this is a mind blower. This is the European Space Agency. That's like NASA. And they are claiming about space this right here, cosmic microwave background radiation. Well, what does that mean? Cosmic microwave background radiation. Well, radiation is energy, radiating. Cosmic microwave, that's tiny, tiny, tiny energies that are almost insignificant. And it just is in the background. It's in the background of everywhere. It's everywhere. It's everywhere. It's everywhere. So we got these tiny, tiny, tiny little bits of energy that just seem to be everywhere. That's what a cosmic microwave background radiation is. Now, here's what they're talking about here. They call it the fossil radiation. The furthest that any telescope can see was released soon after the Big Bang. Well, let's talk about that. Scientists consider it as an echo or a shock wave of the Big Bang. It's just way, way, way out there. And it's expanding so fast that it's exceeded the speed of light, they say now. They say nothing can go faster than the speed of light except all of this stuff that's way out there. Because it's so slow now, when we look at it, it looks like it must be going a bazillion miles away from us. Now, the Planck mission will detect this first light, which is also the oldest radiation, from as far away as they can see. Now, what is the evidence for the Big Bang? Let's look into this. Okay, my friends, get ready for this because it's going to be true. I consider myself a material scientist. If I can't show you evidence, I don't talk about it. But they're talking about evidence for the Big Bang, and here's their evidence. It says the cosmic microwave radiation discovered in 1965, two radio astronomers in the United States registered a signal that they just couldn't explain. They attributed it to any precise source in the sky. They couldn't figure it out. So it apparently, listen to this, so they just started to accept this. It apparently came from everywhere with the same intensity. It's just like a glow. Day or night, summer or winter, it's just a glow way out there. They concluded that the signal had to come from outside of our galaxy. It came almost from the origin of the universe. Why did they come up with that conclusion? It's just a glow out there. It's just a very light haze of energy. Scientists consider this discovery solid evidence for the Big Bang. Solid evidence. This theory predicted that the shock wave of the primeval explosion was still detectable as a subtle wallpaper coming from everywhere behind all galaxies, quasars, galaxies, clusters, because it's way out in front of everything. Today, the Big Bang model is still the only model able to convincingly explain the existence of the CMB. No, it doesn't explain it whatsoever, and electron flood explains it perfectly. It says, according to this model, the universe started with a very dense, hot phase, expanded and cooled itself. For several hundreds of thousands of years, the temperature was so high that neutral atoms could not form. And then it goes on to talk about really kind of silly stuff. This is all accepted now as reality. And this cosmic microwave background is just light that's gotten so slow that it's just barely moving anymore because it's interfering with all of these fields which I showed you. All of these fields are in space. Anything that goes through there is going to be opposed. The field to field always creates a resistance. It's a resistance to the movement. That's just a fact, and nobody can dispute that. I don't care who they are. All right, so don't forget, this is Science Alert, and then what is the redshift? Now, hold on one second. All right, don't forget this. This is not correct whatsoever. It says the redshift can tell us the distance between us and other objects in space, because how slow is it coming at us now? That's not true. It's what is it coming through? How much density is there? How much fields are in the way of that particle coming? Because it will slow it down. It's like the particle starts like this. And as it comes through, it slows down and 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 down. And then you get to the redshift. And eventually it gets so slow that the particle itself is just sort of drifting around out there. And that's what you call a cosmic microwave background radiation. It's just floating around, these little particles. They're really not spinning at you. They're not being emitted from anything. Well, they did originally, but they've hit so many things that they're just drifting. That's what the cosmic microwave radiation background is. And all particles start out as tiny little particles coming off the sun. Now, they could be coming off in big chunks, little chunks, particles of every single size come off of these suns and emitting bodies. And you can see it. Well, hold on, I'll show you. Okay, this is going to take a second for you to think. All right? What am I showing you here? This is a total eclipse of the sun. Well, an eclipse means you put a dark body, which happens to be the moon, in front of this glowing body that normally you can't see because it's so brilliant you can't see it. So that covers up the brilliance, and then you can see the emissions. All right, and then you can see the polar lines. That's the North and the South Pole, runs right straight through that. Now, what else can we see? It's spectacular, yes, but if you really pay attention to the details, you're going to see there's a little red spot there, there's a little red spot there, and there's a little red spot there. Why would that be? Well, I can tell you exactly why it is. And their reference to the pole. All right, there's the North and South Pole, however you want to call it. Now, these three spots create their own zones of electromagnetic flux. You see them? You see that? All three of them have their own spikes coming out of them. Now, also, is in my opinion, the sun is moving this direction, traveling forward in that direction, and is spinning in this direction. So as the sun comes forward and moving forward, it's doubling its forwardness and then hitting harder here. As it comes this way, it's trailing off, and this stuff sort of sloughs off this side. You can see it's totally different than this side. This is the energetic side. This is the slough off side. But you can see it's rolling itself back. Here it's impacting and spewing way out, boom, boom, boom. Here it's sort of drifting backwards and sloughing off. And like I say, take some time to really reflect on what you're seeing, because this is very stunning. Now, you can almost see border lines out here. You see them? They're almost like shifting the colors. That hue is very consistent. What does that mean? It means these particles are losing energy rapidly as they come out. Where there's a whole bunch of them, they're really getting, but here where you see on the poles, I'm not exactly sure, to be honest with you, what is happening here, but I can tell you one thing. All of these little spritzes are the same thing. These are energetic particles. Now, they're wrapping around here somehow. I don't know. That somebody smarter than me is going to have to figure that out. But my takeaway from this is that the sun's spinning like this direction, like this, and moving in that direction, causing this to be the major parts of the impact that you see, and this to slough off. I think I've made that point. All right, so let's see what else we can determine about this. All right, so I mean, obviously the universe is completely saturated with these particles. Even Fermilab says that. They said it's a quantum foam. Look that one up, Fermilab quantum foam. It talks about all these particles in space, which are light and dust and everything else. It's just saturated with particles. There's no way in the world that light cannot slow down. And here, I never say something that I can't prove. Let's look at blue light actually slowing down. All right, I showed you light speeding up. Here's a blue light slowing down. You see, it's coming in this way. And it's spinning. They spin just fast as you can be. Now, it's drifting to the left means it's spinning to the right. Again, give it some time to bounce off your mind and think about it. If it's drifting to the left, it's spinning to the right. Now, here you can't see two white spots. You see one. White, and it's almost coming perfectly straight. It's so fast. It's really fast, and you can see how tight it is. And here it starts to open up, and this is what you would consider a red shift. This is blue light shifting towards the red, and now you can see that there is two little particles there. Back here, you can't see it. You never even know it. That's why blue you really can't work with. It's just too much energy. Even the green is very, very powerful. But the green you can see just like the red. I think I showed you before the red having its neutrino phases and then turning into the photons. Same particle. Only green is much more powerful. And that I can show you again. Again, no claims unvalidated. All right, look at this. And this is, I can guarantee you right now, this is the first time anybody in the world has ever seen light spinning in this direction. All right? Light spins like this. If it's going forward, it spins like this. It doesn't spin like this. It never spins like that. And they know that. It's called upspin and downspin. It's like this or like this. And this one here is tumbling. All right, you should be able to see that. Let me home in on that. And it's tumbling. You see it tumble? That doesn't happen. That just never, ever happens. And the only reason it is because of this energy field going so fast that it's pushing these things out of the way and making them flop this way. All right, because the green is right above the red. They're coming through the same slit at the same time. And you can see the green react way out there. It's reacting way out there. All right, because it's just so much overwhelmingly powerful and pushes the red out of the way. And it is the same particle. You see, here it is right here. You can't see it as well. The ones Rodney did, you know, he used a Samsung Galaxy S3 phone, which has some very, very excellent CMOS in there. Because all of these were done. Rodney did all of these. Well, 90% of them. And again, look at how perfect that is. And you can see the particles spinning. And you can see all these little separations in there, which means they don't want to touch each other. The white ones hate each other. The black couldn't care less. It gets right on top of each other. All right, and you see it right here. The white ones, when they push each other, they glow. And this is feedback from this literal explosion. This is basically, and I'm not kidding you, I'm not kidding you at all. This is a subatomic nuclear explosion right here. I'm telling you. It's this fission right here. All right, the black is separated from the white, and fusion right here when it comes back together. And that's what nuclear explosions are, fusion and back to fission. And that's what happened here. This particle accelerated until it exploded, because the white is the only gooey part that can squirt through there like water. The black is like a bowling ball. And the beauty of this is that the black keeps slapping the white and making it squirt harder and harder. Now let me get up real close to this so you can see these black balls, because those are the sterile muons. The white is an electron shower, and that's pretty obvious. The sterile muons, I need you to understand, those are dark matter. All right, so here it is right here from CERN Fermilab. They looking for these muon neutrinos, which is the black ball, to turn into a muon, from the neutrino phase to just a standard muon, and from the electron neutrino phase, which was the white ball, into a shower, which is here. Now, here's the black ball. You see them right there? I'm going to home way in on this. But don't forget, the black ball just stays the black ball. They were black and white attached at two little bar magnets, and a muon, which is the black ball, is dark matter and dark energy. It has all the weight and it has all the mass, basically. These have almost no weight whatsoever. The electron showers have zero weight, basically, and they have a ton of energy from the fields. I can't explain that. It's just true. And when you shove these white particles into your battery, you're not adding any weight to your battery, but you're adding all this energy. And we should be able to do this very, very easily, I think. Now, what you see all these black balls? The only reason you can see those is because there's a dark matter. They don't emit, they don't reflect, they don't absorb, they don't do anything. All they do want to be is attached to the white. So you see them laying over the top of the white. Otherwise, you'd never see them. And the only way you can see them is when the black gets on top of the white. Here we're looking at the white. They're behind here. They're all mixed in, and they're trying to jump right back in here as quick as they can. But this is fission. Right here, the black came away from the white. There's no question about it. And you can see the black doesn't mind being right on top of each other. They'll just glob right together. The white says, get away. That's why you have all this spray. These are repulsion patterns. They're not floppy waves. This is one single slip. And it's coming out of here, and the white says, get away, get away. And they all move apart. And then you get all these little stripes they call interference patterns. They're not interference patterns. They're repulsion patterns. And that's what drives all those little, right here, you can see them perfectly. Those are repulsion patterns. And then they form like little balls here and there where there's the most of it, I don't know, I can't really explain it perfectly, but I can tell you what, that's the red lights, the red laser screwing through that Venturi. Okay, it's insane to think that there's not tons of particles in space, and that the thing's coming from way back here, that light, it has to come through here. It's coming through, it's being blocked, it's being resisted, it's being slowed down. I've shown you light can speed up, light can slow down, there's no question, and eventually it will get so slow it becomes what they call the cosmic microwave radiation background. So now, not only is it the cosmic background, which you can't see, it's just barely a glow in the background. It is all of these other particles that everything has to spin through and scrub against. That creates our global warming and the sun's corona. And the more we blow up the gases, which we're blowing them up like crazy, and all these fires that are going on around the Earth, it's expanding the Earth's envelope, making it harder to scrub, making the extreme weather events. All right, picture this. We're one of these stars somewhere. It's going to be our sun. And all of us are going to be conglomerated around it as the planets and so forth. And then there'll be a division into another solar system somewhere. They're all over the place. I mean, obviously, every one of these could be considered a sun. So we're on one of these arms moving, spiraling through the galaxy, the Milky Way. They're all basically similar spinning particles. Now, what does that look like if you were in one of these arms? It appears it would look like this. All right, so now, what do we have? We have the sun leading the pack. All right, we're all trying to catch up to the sun. It's spinning like this. All right, see, and it's scrubbing its particles off, as we saw during the solar eclipse. We could see that. Now, what else is going on here? All of these planets are spinning behind it. So the sun is scrubbing through everything that's in front of it, because everything is in front of everything else. You got to scrub through it. So we have to scrub through not only that stuff, but the stuff that the sun is spewing out, which is the solar radiation that we're running into all day long. So the harder that sun hits whatever out here, the more it glows, the more we're going to glow, because we have to plow through that particle as well as whatever's out there on top of it. So that's going to influence weather patterns, absolutely. But the other thing that's going to influence is how big is our footprint coming through the space. The smaller it is, the less energy. And the bigger it is, which means the more it the more expanded our atmosphere is, because all it is atmosphere. Way out at the edge of the atmosphere is the ionosphere and the magnetosphere and so forth. They call them all kind of different names, but the interaction in that layer around the globe is where we scrub. And you could call it the ionosphere. If you're religious, you could call it the firmament. That's fine. But what it is, it's a surrounding right here. Here's what it is. And so every planet has one, or every body has one that's in space. Because the electron portions, the glowy parts that we can see, all these things in front of us, they want to be stuck to the Earth. But they have energy, electrons in front of them. This is always going to have the electrons coating the core, and so there's a lot of dark energy inside the Earth. There's a lot of dark matter, it appears to me, because everything falls to Earth. That's what gravity is. Now, space is completely saturated with particles. So as the sun spins and scrubs through space, as I showed you, its way out here is this, what they call the corona. And the corona, its particles that are sloughing off are now hitting space, and here's where it's millions of degrees out here. It's only 10,000 on the surface, only 10,000 degrees. Way out here it's millions, and they have no explanation for that whatsoever according to their theories. And they have no explanation for why it's 3,000 degrees out here. Our ionosphere in that area way out there where our scrub zone is, I call it the scrub zone. And this is the scrub zone for the sun. It's just the sun is so massive, the scrub zone is incredible. And we're not quite as massive, but we're blowing up our atmosphere. And the bigger it gets, the more the turmoil and the more the scrub is on that. And that's your weather patterns are created out in these scrub zones. And there's some terrible, terrible situations going on with our weather patterns. If we don't reduce that scrub zone, we're in trouble. And the only way to do that is to stop burning things that expand. Every time you burn something, exponential expansion, absolutely unbelievable amount of expansion gases. And, you know, and I'm not sure they fully understand that that's the problem, is the expansion. And pollution in the air is bad, yes, absolutely, but it's the expansion of the gases. It makes a scrub harder and harder, which gives you all these tornadoes and hurricanes and compressed air, which causes extreme floods and condensation in areas. And, you know, there's going to be all kinds of uplifting and welling and everything all over the Earth. And it's exactly what's happening now. There's going to be spots that are just completely dry. I was just looking at a map of, I think it was Australia, and the fires that are burning there, just absolutely unbelievable. I think it looks like the damn place is on fire. Yeah, see, this is that science alert again. I watch all their stuff because they try to give you all the latest that's being shown. But they always rely on peer review, and so I post my stuff basically against their stuff. Now, but you know, it's very interesting. They do some good research, and I'm not going against them. I just want to be part of the conversation. Now, they're showing a haunting animation, shows all the fires burning in northern Australia the past 2 months. There's a lot of issues we have right now with the climate, and because of this expansion gases. And if we could get free energy, and I think we can, and it's as simple as this. Well, I say it's simple, but it's something to take a look at. Let's go with that. All right, here we got this. We got just completely white energy. That's exactly what you get when you end up pumping something into a battery. This is all you want to pump is this. And we're just pumping it by hitting the venturi. We didn't do anything, nothing. The laser forces that to convert into the white. And we can do it with the green and the blue. There's no reason we can't do it with all the frequencies. And we can take a harvester right here, just right here, and run that down through a photodiode. Means it can go down through, the photons can go down through, but nothing else. And they just collect in the battery. You go driving around, do whatever you want. And you should have tons of them. You should at least have 200 times more than you started with. That's not bad. Somebody's got to look at it. Fission, fusion, that's white electron plasma. All right, doesn't get any better than this. All right, don't forget this now. They're saying that it's the second thing Redshift can tell us is the distance between us and any object in space, basically. And they're saying it seems that they go faster rate than those closer. So the further away they go, they're moving faster and faster. They really can't account for any of this. So at the end it says all explainers are determined by fact checkers to be correct and relevant at the time of publishing. Text and images may be altered, removed, or added to as an editorial decision to keep information current. Well, again, they go with peer-reviewed stuff. If it's not peer-reviewed, they don't consider it to be valid. I'm showing things that they don't want to peer review because they won't review them. Because I have too much evidence to support what I'm saying. I mean, I've shown you things that nobody can show anybody. Light accelerating, light slowing down, everything in space is a dipole. They're all dipoles and there's fields everywhere. We know that everything coming through here, these are all dipoles. And anything that spins in space, and the moon doesn't spin, so it's not a dipole, but it crushes. And that shifted this stuff to blue. And I can explain the auroras. I mean, well, I can explain those too, but I can explain the corona and the ionosphere, the temperatures way out there, and all the temperatures here. See the atmosphere layers. All right, here's a minus 80 degrees here, and guess what? Up here, it's high temperature 1500 degrees. Why? It's actually got higher than that out there. I think they must be talking about Celsius. I don't know. I think it's like 3,000 degrees at the outer ionosphere where you scrub. When you scrub, that's where you get this ionosphere. Ions means extra electrons. And this is where your meteorites and all that stuff burn up, and the heavy-duty stuff coming through is supposed to get filtered out in there. And then it gets down to minus 80 after you come down here. All right, and there's the layers of the atmosphere absorb different particles, put it that way. And that's why you get a lot of electrical energy out here, the ionosphere. And it's high temperatures. And then immediately below that, you get all your real cold temperatures, minus 80 degrees. And then down here it starts to level out, and then you get, surface temperature on the Earth. See, they don't even understand. Light is a spinning particle. They say this is, again, European Space Agency. Light is, after all, a wave, just like waves in the sea. No, it isn't. It's a spinning particle. I show that. I can show the things I'm talking about. They just have come up with these statements. Here's NASA. They're just as bad. The electromagnetic spectrum. As it was explained in the introductory article, Electromagnetic Spectrum, electromagnetic radiation can be described as a stream of photons. I'll go along with that. Each traveling in a wave-like pattern. Well, if you can see them sideways, it looks like a wave, but they're really traveling like this. Some of them slow and long, and some of them fast and zip, and having a lot of angular momentum, which gives them a lot of mass. Now, they say each traveling in a wave-like pattern, carrying energy and moving at the speed of light. No, the speed of light is not consistent. In that section, it was pointed out that the only difference between radio waves, visible light, and gamma rays is the energy of the photons. I'm okay with that. Radio waves have photons with the lowest energy. Cosmic radiation background is basically the same sort of stuff. The microwaves have a little more energy than radio waves, but not much. They're just sort of floating around out there because they've lost all their energy. And then you get into microwave, have a little more energy than radio waves. Infrared has still more, followed by visible, ultraviolet, X-rays, and gamma rays. And you get to a point where you got black body radiation, which has no more electrons. We can get into all of that. And then they talk about radio waves and what they have to say about it. But here's the key. Everything's based on the wrong assumptions. This is both the speed of light, which I can show you and have, is variable, and Planck's constant are constant. No, they're not. Absolutely not constant whatsoever. They can speed up, they can slow down. Just like I showed you, the light, the blue light, coming in like this, slowing down. That's all. And the other one, the red, sped up. It came in like this, and it came in like that, and it's sped up. All right, and rocket ship through there, and that gained energy because of its speed. It's going the other direction. It started out like this, and it goes, and it started stacking up on itself, gaining energy. So they never change in value. Totally wrong. Absolutely unbelievably wrong. And this is NASA. And then they're talking about astronomy across electromagnetic spectrum. I have things to show them that are so spectacular, and they refuse to engage. So what do you do about that? All I can do is keep posting. But I can see all of these different frequencies and all these different spinning particles. They're not waves like that. All right, they are spinning particles like this. All right, and like I say, and here it is, the blue particle. You can see that's a spinning particle. And I can show you. Well, let me show you the red ones too. I got other ones, and every time, the harder they hit something, the more they glow. The glower they are, the more energy they're having. And I'm going to show you them interacting with their own selves. Okay, you remember this one. And remember all these little bits staying away from each other. Now, here's what these look like from the side. You see them coming here? You see where they're getting close to each other? They get real glowy. There's a whole batch of them coming together here. They don't like that. They want to lose their energy, or they want to gain back to the black and start life again back as a complete particle. But here they're just glowing like crazy, and they don't want to be next to each other. They stay away. The black can glob right onto each other, and it's starting to try to catch in to all the white particles. You can see them. They're trying to get back together, and then the Higgs fields will start to flow out of here. All right, this is what actually ends up happening. You get these Higgs fields. Those are the little white spritzes, see them? They come and bang, and they start to make all these little spinning disks. Okay, we're looking right into the Venturi at this point. So I showed you from the side view here. All right, and coming from behind, creating the pattern, and then to the fields. And if you looked at it right exactly where the white, this is a very, very tight focus. It just created all that. Now you see these little white strips, you see that little strip hitting right there? You see it? You see that little spot right there? When you see it hitting there, you can almost see the black and the white, and it doesn't continue on. It's making this field, I believe. And I'm seeing them happen everywhere, where the white is hitting the whites here, and they're spinning, and they all seem to be spinning in the same direction. We did find one that spun in the wrong direction, and that one was right here. You see how this one here is coming up here and hitting and spinning this way, and they all seem to be spinning this way. That one there itself appears to be a particle, but it's not spinning in the correct way. And then that interacted and created some really, really, really strange, well, I understand it now, I think, but it appears to have been a reverse spinning particle. I'm almost certain of that now. All right, this is beyond cool. These are spinning disks. All right, they all spin, supposed to be what they call a right-hand rule. And they spin in one direction, supposedly. All right. Now, this little white particle right here, I believe was the one that I showed you before that I said was spinning backwards and gathering its field. And I believe that's what's happened. And this has its own field to speak of. Something's going on here. You see the white little spritzes coming out of this, and it's interacting with this field that it hit right here, which is a normal field. So this one here is coming this way, spinning like this. Now, if this one come down and it was spinning backwards like this, in other words, this one's spinning this way, this one's spinning that way, what would happen? I think exactly what would happen happened. This is the particle. I believe the particle rests on the outside edge of these spinning disks. That came by this way. As this was banging into this, and as that banged into this field, it stripped the particle off. Right here. It banged right into that particle and stripped it off and spun it. I don't know whether it's spinning it backwards or correct ways now. I don't know. Or is it going to get bigger or smaller? That's about the strangest one I've ever seen. And I've seen thousands and thousands of pictures. And that right there, that one blew my mind. And all I can say, it is what it is. And I believe that was that reverse spinning particle. And it would account exactly for this. If this was spinning in this direction, and this was spinning in this direction, when they click together, the particles against a particle, this one being the more powerful, probably strip that one off. That's my interpretation. Okay, I'm going to wrap it up at this. Both the speed of light and Planck's constant are constant. They never change in value. That is from NASA. And in the European Space Agency, they think the same thing. I have shown you that is absolutely not true. The speed of light is variable. It can slow down. It can speed up. I have shown both of those things very, very clearly. And I can show that the white separates from the black. That's fission and that's fusion, very, very clearly. And this is pure electron showers, and these are the black muon balls, the muons. And that is the dark matter and the dark energy. They've never taken it into account as that. All right, they're just looking for it as a particle, but it is the dark matter and the dark energy. I've shown all of this stuff very, very clearly. And I don't see how anybody could not want to look at this deeper. I think it should be taken into consideration and looked at deeper. And I think that these are assumptions, depending on assumptions, whether space curves and all this business, and they won't look at what's right in front of their faces. That's the killer. And then they make statements about like this that says all these are determined by fact checkers to be correct and relevant at the time of publishing. But that's because they have to be, everybody has to agree. Now, that's fine. I'm good with that. But can I comment? No. I'm never allowed to comment on any of these things because my comments don't fit in with their dogma. All right, and once you're in that right realm and you start talking about something like me, you're in trouble. And a lot of it has to do with my work in the Mudfossils, and that's all been validated by Yale and everybody. They agree 100%, but nobody talks about it because it throws everything off for them. These exceptionally, well, here it is right here, hold on. I keep showing this, but I am going to keep showing it because this is what I originally was into, these exceptional preservation of soft-body creatures preserved by silica-rich oceans. There was a great flood. There's no question about that. And this goes back years and years ago. This goes back to 2016. I published my book in 2015 and my paper about this after nobody would respond to it, and then basically Yale took credit for it. And these are the kind of things that happen all the time, and they're trying to get the light research under their own umbrella too. But I have papers that go back to 2015 on that, even earlier than that, about dipole electron flood theory. So hopefully this would be looked at, and maybe we could get some free energy. That would be really nice to try to turn things around a little bit. Okay, my friends, so as I have shown you, the new model is dipole electron flood theory, and everything is made out of dipole electrons. And the cosmic microwave background radiation is not correct. It's just slow light. Speed of light goes up, it goes down. It's just slow light. In addition to that, the redshift is not correct. The redshift is just light slowing down and turning into the cosmic microwave background eventually. Expansion of the universe is now highly in question. If they think all of this happens just because the universe is expanding and that supports the Big Bang, all of that is a house of cards now as well. So I love you all. Let's concentrate on what I have shown, not what you're being forced to repeat in schools. Let's talk about what this evidence supports. And it supports everything that I just said. Light is just slowing down. The redshift is wrong. Anyway, I don't want to, just belabor it, but it's true. Nobody listens, so it never gets. The word doesn't get out. And even when the word gets out, they don't. It's hush hush. They won't respond. And that's what I found right across the board. So unless somebody starts to speak up to your professors and say, "Look at what this guy's showing. This is evidence. This is not just hyperbole. This is something with some substance to support it." And I think there's some possibilities here that could help everybody. And if that's the case, I feel like we're missing the boat here. All right, I love you all. Talk to you later. Talk to your professors. Talk to your friends. Talk to the people that they think they're all the science guys. Everybody's got a guy around that hangs around like me that, oh, I know this, I know that, Well, talk to that guy. All right, I love y'all. Bye.